then another ring, let me denote it as R, and then homomorphism is given as follows. Just I will take 1 and I take its image, additive homomorphism. So this is a identity of R. So now what we have as a result. So it is enough to demand additivity. So f of A plus B is f of A plus f of B. This plus in Z, this plus in R. Multiplicativity easy to get from this because M is written as 1 plus etc. plus 1 M times the same N is written 1 plus 1 etc. N times, and the Mn is written again 1 plus 1 etc. M plus N times N, M times N time. So if you apply this additivity property, then the image of this will be the image of this plus the image of this, no problem. So sorry, for multiplicativity. So I will get Fm times N is Fm times Fn. This product in Z again, this product in R. Okay, so now the kernel of this homomorphism definitely is an ideal in Z. But all ideals in Z, we know they are from N times Z. Yes, all multiples of Z. Okay, now first one, what can we observe from this? Let us now consider R, let R be a field K. A field K. In that case, I claim that this N must be a prime number. Then kernel of homomorphism F is given as a P times Z, where P is a prime. Why? Because if N is not prime, then it will be given N is written, if it is a composite, then N is written as N1 times N2 as a product of 2 less than N numbers. Then if I apply this F to this N, then what will get? What do I will get? So it is F of N1 times F of N2 which is 0. From where I will get at least one of these two is 0. F of n1 is 0, or f of n2 is 0. If n1 is 0, that means n1 is in Zn. Sorry, Nz. Nz means n1 is multiple of n. It is impossible. Why? Because n1, n2, they are less than n. They cannot be multiple of n. If n2 the same, so n2 cannot be multiple of n again. So that means our assumption that n is written as a product of two, n1 and 2 is wrong. It's not correct. So that's why n must be a prime number. If k is a field, here R is a field. Homomorphism from Z into a field K, then a kernel must be PZ, or kernel must be trivial. This is case A. Let me take case A, then case B. Kernel is trivial, consists of only one element, 0. So in this case, when the kernel is PZ, we will go characteristic of this field K is a P. Prime characteristic field. If the kernel is 0, then characteristic of K is 0. So the same which we discussed last time on the characteristic of ring and the field. So if I take field for this homomorphism, then characteristic is P if it is kernel is multiples of some prime P. That P is called characteristic of the field K. If the kernel is 0, if F is monomorphism or injective morphism, in that case, characteristic of K is called 0. Okay, now I want to just a few words on this case. So I have G. Here, let me write K, a field. Then if characteristic is P, then I have here G over PZ. F is according to homomorphism theorem. Here I have projection homomorphism. I denoted it by. Then there is a H. So you can see here, this guy is a field. So a homomorphism from one field to another field. If you have homomorphism from one field to another field, then this homomorphism is injective homomorphism always. Why? Because if you consider the kernel of this homomorphism, the kernel must be an ideal of a field, but a field has only two ideals. One is field itself, another one is zero ideal. So that we will get such a inclusion of this field into this field. That means we have copy of this field in this field. Okay. All right. Now, now let us consider case K is finite. In this situation, let K be a finite field. If it is finite field, then this finite field can be considered as a vector space over Z over PZ. So V is K, and F there is ZPZ. We can consider some vector space over this field. A can be considered as a vector space over some another field, over a subfield. This is a subfield. ZPZ is a subfield of K. If K is finite, if there are finite number elements in it, then the number of elements of K is given by Galois. It is a P to the N, where N is dimension of this vector space over this. We will see how to define dimension. So Galois proved that if you have finite field's elements may be only some prime number and a power. So prime power, any finite field has prime power elements in it. So this is a Galois result given a long time ago. Moreover, what he did, he proved that if you have some prime number P and the natural number N, then there exists unique up to isomorphism a finite field where that field has P to the power N elements. This is a second part of Galois statement. So thus, what we can conclude from here, if you have a field, finite field, then in fact we know some finite fields of these forms, Z over PZ form. Number of elements of this field is P. So that means we have 2-element field, 3-element field, 5 elements in it field, 7. Next one is 11. Next one is 13, and etc. P elements field. So this is just ZPZ. But Galois says we have the following fields also. 4. Next is 9. Next is so we don't have a one element field there definitely, because it should be 0 and 1. 2 element field we have, 3 1 have, 4 we have, because 4 is given 2 to the power 2. 5 we have, 6 we don't have. We don't have 6 element field because 6 cannot be given as a p to the power n. 7 can, 8 can, because it is 2 to 3. 9 can, it is 3 squared. 10 cannot, 11 can, 12 cannot, 13 can, 14 cannot, 15 also cannot, 16 can, etc., etc. So that means finite fields a bit different from the finite groups and the finite rings, because in groups case, if you consider groups case, if you fix any natural number n, there is a group with order n. With the order n. This is a cyclic group. This is a cyclic group. A to the n is identity. This cyclic group gives you the group of order n. This is groups case. You can see rings case also. If you have ring, then again for any natural number n, you have ring with n elements in it. So that is Gn. Gn. But for fields, you don't have such a situation. For groups, you have, for any natural number group with that number elements in it. For rings, we have. So these are examples. For rings, we cannot. That is a close result. Any prime field has only p to the power n number elements in it. Here, how to get it? According to this, just observation, because K is a vector space over this field, so any element of K will be n coordinates. So it's given as follows. Let me write it: A1, A2, etc., an. But each ai run in this field. So that means for this you have p values, for this you have p values, for this you have p values, and so on. For last one also you have p values. If you multiply, then exactly p to the n elements you will get. So any element of, if you count number of elements k, it's a vector space over this. It has such a form elements. Each element has coordinates, has p values. So that's why overall numbers k over f is p to the n. So that is observation. One observation. Okay, now let us consider. Let us go to vector space now. Vector space, we for vector space, what we have? So two ingredients. One is non-empty set V. Another one is a field F. A field F. Then this guy must have some additive structure. With respect to that additive structure, it must be abelian group. Abelian group. So you will get 5 axioms. 5 axioms. Then combining B and F, you will get another 5 axioms. Let me just go to slides now. So you have these 5 axioms, giving that V is abelian group. Then another 5 axioms, the combination of V and K, elements of V and K. Look at these axioms. They are almost the same which rings case, because this one is like looks like a left distributivity, but instead of element here, you will take element of fifth. So left distributivity. Okay, this is right distributivity, because we don't know how to multiply elements of B. We know only we can multiply elements of B by some number C. So this is C times U plus V is this, or C plus DU is this. So this is left distributed, this is right distributed. This is exactly associativity property. But CD, they are elements of F, and U is element of B. This is like identity property. 1 times U is U, but it's a bit case for adjusted to vector space. Okay, we considered some examples last time. So let me here annotations. Real numbers R2. No, usually real numbers we denote as R. No, it's okay, it's given here. But what does it mean R2? R2 means ordered pairs. This is A1, A2. AI from R. Accordingly, n tuples they are these strings A1, A2, etc. AN. AN, we take it medium. Okay. Then AI in R. Addition is component-wise addition, and the multiplication, any such a string by C means multiply coordinates. This is set of all continuous functions, but this cannot be represented this way. Continuous function defined on this closed interval AB, still you cannot define. I cannot represent this way. We will see why later on. The set of all polynomials, then set of polynomials degree no more than n. Now let me give some examples now. More examples. Let us go our old friends, which is as a V. I will take complex numbers, real numbers, rational numbers, It's F. I can take again complex number because it is a field. Real numbers or rational numbers. So any field is vector space over itself. C is a vector space over itself. C is a vector space over R. And C is a vector space over Q. Then R itself is vector space over itself. And R is vector space over Q. Then Q is vector space over itself. Okay. Regarding that field is vector space over itself. How to understand it? Say, let me take as a V R as a F also R. Huh? R. So, well, what we'll get? We have the following. We have take one element from this, which is say 5. And the element from this, I will denote that element as say 6. But it is all elements of V they are called vectors. These elements of F are called scalars. So I will take scalar 5 multiplied by vector 6. So result I will get vector 30. Vector. Another case, I will take 6 as a scalar multiplied by more precisely, I will multiply vector 5 by scalar 6. Again, I will get 30. No, it is a vector again. So that means when you consider some field as a vector space over itself, scalar you should take this product is product in that F, but one time you will take elements of F as a scalars. So for another side you will take them as a vectors. So product will be vector. This product also is a vector. So that is a case. So now, how about this? C over R. So complex numbers they are abelian group with respect to addition. If you consider complex number multiplied by a real number, result is complex number. Any complex number, if you multiply by rational number, result is complex number. So this is real number. Real number multiplied by rational number, you will get real number. So that's why these all vector spaces. C vector space over itself, R and the Q. R is vector space over itself and the Q. Q is vector space over itself. Of course, you may ask, can we get, say, R as a vector space over C? Definitely we cannot. Why? Because R is a abelian group. But if you multiply real number by complex number, you will get a complex number. You will go out from this R. So that's why this is cannot be given as a vector space R over C. Okay, so this kind vector space, if you consider vector space over C. Sometimes they call it complex vector space. If you have V over R, they call it real vector space or vector space over real numbers. So accordingly, this is over rational numbers vector space. Okay, so of course, what can we do is next one is just you can take that first ingredient, keep as a V. As a F, you can take any ring R. Then impose that axioms. What do you get as a result? You will get a module. So in that case, with that axioms, V is called R module. Or module over this ring R. V is called R module. So vector space is a particular case of modules. If R is a field, then you will get vector space. Because any field is a ring. So that's why vector space, they are a particular case of modules. Okay, next is a few examples. Again, I will take V, say polynomials of two variables, say x and y. Then, as a f, I can take that k. If I take, let me maybe take this as a r. Let me take r. Still can. So let me take any ring r and consider polynomials with a coefficient r of two variables, or vector space over ring r polynomials with coefficients from r with one variable. Then, of course, V is R module over R. Module over R. So R module. Here you have R module. This also is R module. If your R is some k, if R is a field, that is a field, then of course you will get the vector space. V is vector space over k. About this, V over kx because it can be written, this can be written as follows. R of x and y. That means these are polynomials of y coefficients from Rx. So that's why this is the Rx module. Rx module. So V, this, if R is K, still Kx module. Because Kx is ring. Kx module. So conclusion is vector space, they are particular case of modules. If you know module theory, then you know vector space also. Okay, now let's go to slides. So we had last time we had this properties, subspaces. So we have subspace. Let us take from our examples. If V is C, W is R. Subspace. Why? Because according to this addition, it should be closed with respect to addition, and the scalar multiplication. This, if you add any real number, result is real number. And no, of course, you will take F. If you take F as an R, then this guy is subspace of this. The same you can take as a V, C, as a W. You can take, say, real numbers. As a F, you can take rational numbers. Again, this because if you multiply real number to rational number, result is real number. So that's why this together with is space, vector space. This also vector space. That is the reason why W is subspace of V. This W is subspace of V. Okay, so now some other subspaces. So let us consider Rn. And as a W, I will take the following. As a W, I will take, let me take, I will write here. As a W, I will take x1, xn, because elements of Rn is n-tuples, such that x1 plus x2 plus etc. xn is 0. So this is a vector space over R. This is subspace of that vector space. Why? Because if you take two n-tuples satisfying this condition, they are, if you add them again, you will get this. If you multiply some n-tuple satisfying this condition by C, result will be again that n-tuple satisfying this condition. So you can just check it. So y1 and so on, yn. Add these two. If you add them, result will be x1 plus y1, x2 plus y2, that are xn plus yn. If you substitute this into this equation, x1 plus y1 here, x2 plus y2 here, etc., xn plus yn there. So you can regroup x1, x2, etc., xn in one group. Result will be 0. Another group, y1, y2, so on, yn. So result will be another 0. 0 plus 0 is 0. So that's why this guy is element of W. The same if you multiply this by C. So just factor out C. So this summation will be 0. C times 0 is 0. So C times of any element of this form satisfying this condition again will be element of this W. So that's why this kind subspace we have in Rn. This is a system of equations. One equation and variable. So the same you can do for system of equations. M equations and n variables. That is given by matrix A as vector X is 0. It's matrix form. This is 0 column vector. So X is given X is given as x1, x2, etc., xn. A is matrix. Matrix. How many rows? This is by the way, it's a column vector. Let me denote. It's a T transpose. It is column vector. This is also column vector. So number of columns must be equal to number of I have mn, right? M rows and columns. So result you will get M equations, linear equations of n variables. So according to this, a solution of this system of equations, is a subspace of Rn. Why? If you take 2, x1 and x2, this vector x plus x2, also vector. Each of them it has the following form. Apply to this, multiply this by A. By distributive of matrix multiplication, this is AX1 plus AX2 equals, this is 0 plus this also is 0. Result is 0. If you multiply A times CX, again, property of multiplication and the matrix multiplication and the scalar multiplication for matrices, you can write it as C times AX. Or this is C times 0, which is 0. So these two conditions hold. So solutions of this equation, it is a homogeneous equation, homogeneous system of equations. So homogeneous system of equations form a subspace of Rn. Okay, last time we already have seen these inclusions, polynomials, differentiable functions, continuous function, integrable function, and just functions of defined on a closed interval AB. Because if you take two integral functions, add them, result will be integrable function on AB. If you multiply any integrable function by a number, then the result will be integrable function. You can take integral. So here, continuous function. The sum of two continuous function is continuous, and any continuous function you can multiply by a number, result is continuous function. Differentiable function, any two differentiable function. Adding them, you will get a differentiable function. And if differentiable function multiplied by a constant, then you will get differentiable function. No, polynomial function easy. Polynomial functions, adding any two polynomial function, you will get polynomial function, and multiplying any polynomial function by a number, you will get polynomial function. So these all are subspaces of V5, W5, sorry, W5. Okay, we defined intersection of two subspaces. So result, of course, will be subspace, the same as group's case, because x plus y in V and x plus y in W. So that's why they will be in intersection also. Multiplying by a constant C also, again, x times C is in V, and the x times C times x is in W. So C times x will be in the intersection of V and the W. Okay. All right. So what is the span now? Span. We have multiplication by constants. So we can take k vectors, k element from V, and multiply them by C1, C2, and so on, Ck. Result will be an element of V, then add them again, that result will be in V. That element of V, which is denoted here as a V, is called a linear combination of elements U1, U2, etc., UK, with the coefficient C1, C2, and so on, Ck. Okay, now, what we'll do, I will fix these elements as a V1, V2, etc., Vk. Then multiplying V1 by C1, V2 by C2, etc., Vk by Ck, I will run now C1, C2, etc., Ck in F. So result, I will get set of elements in V. So it will be all such V from V such that V is written as a C1 V1 plus etc. plus Ck Vk. But V1, V2, etc., Vk, they are fixed, where Ci runs, they run F. When you run a C1 in F, C2 in F, etc., Ck in F, so you will get some subset of V. So that is subset of V. So this subset has a special name. It is called span of these elements. Vk, V1, and span. This subset is called span of V1, V2, and so on, Vk, sorry. This is subspace. Why it is subspace? Because if you take two such kind elements, you can adding up, you will get in span again. Because if you have V V1, as a C1 V1, CK VK, and the V2, C1 prime V1 plus etc. plus CK prime VK. Add them. Just you can add and factor out V1. So you will get C1 plus C1 prime, C2 plus C2 prime, etc. CK plus CK prime. Ci in F, so the sum also will be in F. So result, if you add them, so result V1 bar plus V2 bar will be in span. The same if you multiply by some number or scalar C, the result will be in span. So that's why it is subspace of V. Okay, now this is subspace. In this case, a real numbers case is given, but it can be given for any over any field. Written as a real numbers, but they can be any scalars. So now we call vector space is spanned by some number of elements V1, V2, etc. Vk, if any element of V can be written as a linear combination of V1, V2, and so on, Vk. In that case, we call V spanned by this set of vectors V1, V2, etc. Vk. So this is a span. Okay, because there in our example you can see span is a subspace of V. Span for any vectors, span of x1, x2, v1, v2. Sorry, let us keep the notation. v1, v2, etc. vk. This is a part of V. If you have this inclusion, then V is span of these vectors. Of vectors x1, v1, sorry, vk. This is a span. Okay, now linear independence and the linear dependence and independence. Set of vectors v1, v2, etc. vk in a vector space V is called linearly independent if this equation has only zero solution in C's, because v1, v2, etc. vk, they are fixed. Only you can change c1, c2, etc. ck. So you will get some equation with respect to c1, c2, etc. ck. If this expression, if you equate to 0, then all these c1, c2, etc. ck are 0. Then we call these vectors v1, v2, etc. vk linearly independent vectors. Linearly independent vectors. Otherwise, if at least one such a linear combination with non-zero coefficients is 0, then this set of vectors is called linearly dependent set of vectors. You can get some example. We can get, let's say, even R2. If you take R2, let me take as a V. V1, I will take, say, 1, 2. V2, say 0, 1, C. These two vectors are linearly independent. Why? Because if I multiply first one by C1 and second by 1 by C2, then I will get the following vector. C1, the first coordinate, second coordinate is 2C1 plus C2. But this vector must be 0. So this is 0, 0 vector. From where I will get, because two vectors are the same if they are equal component-wise. So C1 is 0. Then second one is from this. I will substitute C1 as a 0. I will get C2 also is 0. If I equate this linear combination to 0, then the coefficients C1, C2 are 0. I can take another two vectors, say V1 is 1, 2, V2 is, say, I don't know, 2, 4, see. If as a C1, if you take minus 2, and the C2 is 1, a linear combination of these two will be 0. C1, V1, you can check it. C2, V2 is 0, but none of them is 0. So that's why these are linearly dependent set of vectors. So these two set consisting of the V1, V2 is linearly dependent set. Okay, how to find out it to be linearly dependent or independent? So this equation comes to a system of equations with respect to C1, C2, and Ck just now. I illustrated here. For k vectors, also the same. So then you will solve by using, say, one of the method, Gaussian elimination method. If you, by using Gaussian elimination method, if you can prove C1, C2, etc., Ck is 0, then that set will be, this set of vectors will be linearly independent. If you find at least one non-zero solution of this equation, in fact, this one is system of equations, then this set of vectors will be linearly dependent. Some properties here, set is linearly dependent if and only if at least one of them can be written as a linear combination of others. In that case, you can just choose some coefficients, can get a non-zero linear combination, which is non-zero coefficient linear combination. The result will be 0. Okay, in two vectors case, two vectors are linearly dependent if one is a multiple of the other. So what is the basis? So basis for set of vectors in vector space V, to be basis, you should have two conditions. So one of them is this set of vectors must span your V. So that means any vector from V must be written as a linear combination of this set of vectors. But at the same time, this set of vectors must be linearly independent of vectors. Under these two conditions, you can conclude then this set of vectors V1, V2, etc., Vn is the basis of vector space V. Basis is not unique. Such a set of vectors may be infinitely many in general. It is not unique. Vector space may have infinitely many bases. Clear? Why? Because If you take v1, v2, etc., vn, you multiply each of these vectors by some constant, you will get another basis. You can take non-zero constant, of course. You multiply by some non-zero constants, these vectors, and the result will be another set of vectors, but n vectors again, so that will be again basis. You can be easily check these two property in that case. Okay. If you have some basis consisting on n elements for vector space, then every set containing more than n vectors is linearly dependent, because that vector will represent the linear combination of these vectors. If you say you have one more vector, if S inside of some set of vectors, say, let me add only one vector, v1, v2, etc., vn, it is a basis, then I will take one more vector, w. S is contained in this set. So then this set of vectors is linearly dependent. Why? Because of the following. Since it is a basis, W is written as C1 V1 plus C2 V2 plus etc. Plus Cn Vn. So that means C1 V1 plus C2 V2 plus etc. plus Cn Vn plus minus 1 times W is 0. You see, you can find a linear combination with a non-zero coefficient, because this minus 1 is not 0. Non-zero, at least one coefficient is not 0, you know. With non-zero coefficient, but linear combination is 0. So that's why this set of vectors is a linearly dependent set of vectors. Okay, now dimension. If vector space has bases consisting of n vectors, then this number n is called the dimension of V. It is denoted as dim Vn. But of course, let me a bit correct here this writing. So this is dim. I used to put here F, of course. Fv is n. Because dimension depends on this field F. We will see some examples. Let me give some examples. So Rn has dimension n. Dimension of Rn over R is n. Let me ask another case. Dimension of Rn over Q more simple case. Dimension of let me write first a few cases. Okay. So I want to know what is this dimension? Do you have any idea? Let me start from here, maybe. This dimension. What is this dimension? R over Q. Anyone? It's not slipping there? Are you around? Hello? Hello?
Yes, we are here, teacher.
Okay, so can you tell me what's these dimensions? So C over R is 2. So that means we need to find two linearly independent vectors, and a vector is written as a linear combination with real coefficients of the two vectors. So they are, in this case, so V1 is, they must be complex numbers. So V1 is 1, V2 is I. C, one choice. So any complex number is written some real number multiplied 1 plus another real number multiplied I. So I will get A plus BI from expression. They are exactly complex numbers where A and the B are. Let me write 1. How about this case? Any idea for the dimension? R over Q?
The dimension of this, in this case, is 1, I think.
Is infinity.
Oh, infinity. Oh,
yeah, because you have, let me take such a vectors. Say I will take 1, say square root of 2, say square root of 3, square root of 5, etc. So the square root of P is a prime number, say, because the number of primes are infinity. So this infinite number of vectors, they are linearly independent. So this is a linearly independent set of vectors. But they are all in R. So you see, at least I have one linearly independent set of vectors containing infinitely many vectors. You cannot cannot just cut out from here, because if you just cut out here, then next prime number, which is given after this P, cannot be written as a linear combination of this. So that will be problematic. So that's why this dimension is infinity. How about this? This is definitely is infinity again. How about this? This also is infinity. Why? Because we have infinitely many polynomials. Here, linearly independent. They are 1, x squared, x to the n, etc. So this dimension is infinity. Okay, let us go to these examples. Pn. So that means we have polynomials, degree no more than n. We can choose a basis here, by the way. So they are 1. I'm talking about number 2. 1 x squared, x to the n. So this one is V1. This is a V2. And this is a V3. This is a Vn plus 1. So they are linearly independent. And any polynomial of degree no more than n is written as a linear combination of this, because that polynomial can be written as follows. A0 plus A1 x an x to the n. So any polynomial of degree no more than n can be written in this form, but these vectors are linearly independent, because if you take a linear combination of these vectors equate to 0, you will get some polynomial. So c1 plus c1x plus cn x to the n is 0. What does it mean? Identically 0. Identically 0 means for any value of x, it should be 0. If x takes 0, you will get c1 is 0. Taking c1 is 0, then take here, just take 0, this takes 0, then factor out x, and assuming that x is not 0, cancel x, start from c2 now. Again, substitute x is 0, you will get c2 is 0, etc. So eventually you will get cn is 0. So this is identically 0 if and only if all the c1, c2, etc. cn, they are 0. Sorry, here c0 must be right. This is c1. Okay, so result is 0. So this is linearly independent set of vectors, and any vector is written as a linear combination of this vector. So that's why it is a basis. Here we could find n plus 1 vector, which form a basis. So that's why this number of vectors is called dimension. So the dimension of this is n plus 1. The dimension Pn is n plus 1. Dimension of Mn, they are matrices. Dimension here is m times n, definitely. Dimension n times m. Okay, so linear transformation now. Linear transformations. Here, by the way, how to you may have infinitely many bases for vector space. Here it's given 2 basis case, but the number of basis vectors are the same. That number is called the dimension of vector space. So B consists of n vectors, B prime also consists of n vectors. Now, from one basis, you can pass to another basis. You can express one basis vectors via another basis vectors as follows. That matrix here is called transition matrix from basis B to from basis B prime. So it can be found as follows. You will take n to n matrix. You write here that the coordinates of this. Here we will write a coordinate of this. You will write here, coordinate of this right here. Then by using Gauss elimination method, Gauss-Jordan elimination method, bring it to matrix of the following form. So the P minus 1 will be transaction matrix from B to B prime. B to B prime. Okay, so linear combination, what does it mean? Linear transformation, sorry. So you have 2 vector space over the same field, V and W. Any function, such function, is called linear transformation if 2 of these conditions hold. That function must be additive, Tu plus v is tu plus tv, then tc times u must be c times tu. So these two conditions define for a function from v to w to be linear transformation. Please pay attention. This addition is given in v. This addition in w. This multiplication by scalar is given in v. This multiplication by scalar is given in w. So that is important. So that means function t from v to w preserving structure of vector space, because additive structure in the multiplication by scalar structure preserving property these two. Then this function is called linear transformation from one vector space to another vector space. So this linear transformations has the following property: 0 sent to 0, the inverse of a vector v with respect to addition sent to inverse of the image. For the difference, you have difference of image. If you have a linear combination of some vectors, applying to this t, you will get such a linear combination of image of these vectors v1, v2, and so on, vn, with the same coefficients. So the image of this linear combination with coefficients c1, c2, etc., cn is the same with linear combination of their images. So image of v1 is the image of v2, etc., the image of vn with coefficients c1, c2, and so on, cn. Here, given some examples, let me skip that example. Linear transformation has the kernel. The kernel means those elements of v going to 0 in w. That is a kernel, as usual. Here also you have a kernel. Those v from v such that tv is 0. 0 in w. This is a part of v. It is subspace. It's a subspace of v. There is an image of linear transformation. So the image is defined as follows. Already as an image of function. This is those w from w such that there exists v of v giving this w. W is t of this v. This is the image. No, just usual image for functions. This is subspace of w, because this is a subset of w. It's a subspace. So the kernel is subspace of v. The image is subspace of w. Let me skip rank and the nullity. Then isomorphism of two vector space. Vector space v and w are called isomorphic if you have a linear transformation from one to another one, which is bijection. Bijection. Any two finite dimensional vector space are isomorphic if and only if they have the same dimension. So that's why Isomorphisms of vector space are easy. If you take dimension n, all vector space with fixed dimension n, they are isomorphic. So that's why you have only one vector space Rn, real over real numbers Rn. All other vector space dimension n over R, they are given by Rn. So they can be identified by Rn. So you have a Cn n-dimensional vector space over C. All are isomorphic to this. If you have any field F, any vector space dimension n over this field F can be given as a F to the n. They are vectors of the following form: V1, V2, Vn, where V from F. You can choose a basis here, standard basis. 1 here, all others 0. 1 here, others 0. 1 in third place, others 0. In the nth vector, basis vector is 1, and the last coordinate is 1, others 0. That is called a standard basis for such kind of vector spaces. So any vector space of dimension n can be identified by Rn over R over C, can be identified by this, over any field can be identified by Fn. So isomorphisms of vector space easy, nothing to do. You in fixed dimension n, you have only one vector space Rn over R. Over C, you have Cn over F, and you have Fn, nothing else. If it is infinite dimensional, that is another story. For finite dimensional case, you have only one vector. Okay, any questions, please?
No.
Any questions?
For now, we have no questions.
Thank you. Thank you for your attention. So next week I will start to discuss algebras and the classes of algebras. Please be active. Thank you.
Thank you.
Thank you. Have a nice weekend.
Thank you, Prof.
Bye-bye.